Hello everyone, welcome to this session on a program lab program, which is basically how you you should be drawing a three-dimensional Sierpinski gasket. There are many ways actually to draw Sierpinski gasket. This method, what we need to use here is in the program, it is specified that we need to recursively subdivide a tetrahedron. So this is one of the method. We call this as the polygon and recursion method. There are other ways also by which we can draw a Sierpinski gasket. So now we'll see what exactly. So what I've drawn here is just to understand how a Sierpinski gasket looks like. So first here we always start with a triangle here and we divide the triangle. So if you see here when n is equal to 0, there's a triangle here. So the triangle here we have taken a midpoint of all the edges here. So the three edges, we first calculate the midpoint and then we connect those midpoints basically, which will again form triangles. So how many triangles are being formed after first iteration is, so if you observe in the second image here where the n value is 1, so I have marked here one is the inner triangle which I have kept it empty here and I have blocked here with markings. So those are the other three triangles. So how are we going to recursively subdivide is, first we are going to find out the midpoints of the edges of the triangle and then connect it. So what do you get is you get four triangles again. Now you have to forget about that center triangle which I have left it empty without any blocking or any marking. You have to leave that triangle and consider the other three triangles. Let me show you. So that is this one, so this one triangle. Okay. So this is one triangle, this is another one, and this is another one. So this triangle, middle one, we must not be considering. So for the next iteration, what you're going to do is, now what we did for this one triangle, considering the midpoint and dividing, so that same recursively we have to apply for 1, 2 and 3. Don't apply to this middle triangle. So now if you look at this third type wherein your number of iteration is 2. So if you see here, I have not used this inner triangle, the middle one. I have subdivided 1, 2, 3. So now again I got 3 more triangles. Now if you go deeper into the recursion, what do you do? Again forget about the center triangles. Now according to this part, this is your center triangle. Forget this and subdivide this other three. Forget about this yellow middle one and subdivide again the three. This orange one, forget the middle one and subdivide again the rest three. And this is how you look like. It's like, and the more deeper we go, it looks a very the kind of image we get, we call it as a Sierpinski gasket, which is basically a three-dimensional object. So if you see here, the final output here, here the number of divisions we have considered is I think 5. So just look at how beautifully our Sierpinski gasket is formed, and here don't get confused, actually there are see, one face is the one which you can see here in the red, another is the blue one, and the bottom one is the black one, but behind what you can see, the green one, that is that fourth face. Okay, you are actually seeing the front part of it. Okay, you're not seeing the back. I told you already in the cube rotation. Okay, when you're talking about a surface or like an object face, you will be identifying with the front face as well as a back face kind. So it is like we have kept the transparency here so that this fourth face is also visible. And here what does the program say? It says that we need to use a tetrahedron and subdivide it recursively. So this is how a tetrahedron looks like an inverted pyramid kind. It has this one common apex where all these edges are joined. So it has totally four triangular faces. I actually had got and model prepared out of one of your friends only. She had prepared this model. I had actually thought of explaining keeping that model. That would have been better to understand. So you can just Google it and see how a Sierpinski gasket looks like. Then you will understand it in a better way. So this program is, we are taking a tetrahedron and using tetrahedron we will be drawing a Sierpinski. So a tetrahedron is a polyhedron which has four triangular faces. Okay, just remember it has four. We need to draw four triangular faces. That is four triangles. It has six edges and four vertices. That is vertex edge points. So now let us see what each program. So since we have to draw four triangles here using this point V, vector V, we have defined all those vertices of each of the triangular four triangular faces. And here n is nothing but this n is to specify the number of divisions. Okay, and this triangle function, what it does is it basically draws the triangle. So whenever we need to draw a triangle, we will be calling this triangle function. And if you remember here, it is not only for the polygon faces, we are not only drawing the triangle. Every time when we are subdividing it, even then actually, even at that stage also, we need to draw the triangle. So it is not just four times in the tetrahedron we are calling, many a times our triangle function will be called. So within a triangle function, nothing much is happening. We are passing our ABC points, the 3 points of the triangle. We are using the GL begin and passing our GL underscore polygon and using our GL vertex 3F function, and we are passing it in the vector form. So we are giving it as 3F V here and the GLN. So what does our divide triangle do is, just now I told you we have to find the midpoint of every edge and then we have to connect, I told you. So to find that, that is the midpoint, we are using this divide triangle. And here since you may initially start with only three edges, you can ask me why here we are using three for loops. We may start initially with the three edges, but that is with a single triangle, that is for a single face, you will be performing or you will be finding out the midpoint. And as in when you're going deeper for the total number of ends, this have to be repeated, and your divide triangle will be called recursively here. You are basically calling this function in a recursive way here. How many times are you going to call is that is the number of times you need to basically divide. So in the first time, if you look at this image, just going back to this image, see here. So if you look at this, say when n is equal to 1, so here in this case, not much happened here. Midpoint was found only once, but here if you come to n is equal to 2, so here again 3 times midpoint is found, here again 3 times, and here again 3 times the midpoint is found. So in this way, recursively, your divide triangle function will be called. So till you first you will be only plotting the points, and once all the plot points are plotted, only then you will be drawing the triangle. So when you will be drawing the triangle is once your number of divisions becomes less than 0, you will not draw the triangle. After that you will be drawing your triangle. And here, what is this tetrahedron is? To basically draw that tetrahedron, what I showed you, that inverted pyramid kind of object. So it has four triangular faces, and here, for us to understand the faces in a better way, for each of the face, we are actually assigning a different color. I showed you in the beginning in our output. One has a one face has a black color, the other has a green, the other has a blue. So in this way, for each of the face, you will be basically assigning different colors here to differentiate. And again, this in display function, you are activating or you are specifying this buffer, that is the depth buffer you are setting here. The reason is, since this is an 3D object, we need to set this, and even our color buffer and load identity. Whenever any kind of projection is happening, we always load our identity matrix, I told you already. And then this tetrahedron is just a function call, and GL flush, we know that whatever that is to make sure all the calculator or whatever pixel values are there, everything needs to be drawn properly. So we are using our GL flash here. So reshape, already in the previous programs I've told you many a time. So why are we using this reshape function is basically to maintain that aspect ratio. So say I'm using, say now I have drawn a square. Say when I enlarge my window, my square should not look like a rectangle. Even though my graphics window, I increase the size, I reduce the size, whatever distortion is done to the window, distortion should not happen to my image. My square should look like a square only, and my rectangle should look like a rectangle only. So that's the reason we are using our reshape function, and making sure the aspect ratio is basically being maintained. And here in the main function, nothing great is happening. We have just taken the number of divisions from the user and specified a buffer as single. The coloring mode we have set as RGB, and we have activated our depth buffer here and created a window. And again the reshape function, these are all the callback functions. It is not that it is like in a particular order. This is something like whenever that particular action happens, these are being called continuously. And this is our display function. And you have also enabled our GL underscore depth test, wherein you any such depth comparisons happen, you need to keep on updating your depth buffer. And GL clear color, just to set your background color. And then your glut may look any such OpenGL function to make sure that our graphics window, it remains for a amount of time for us to view the output, so that it should not be if you don't use a glut main loop, what happens is it displays, and just within a fraction of second the output is gone. It is not we are not able to even view that output. So for us to perceive that human eye to perceive, and for the graphics window to be on the screen only, what we do is we use the glut main loop. So till you press any key, like an exit key, escape key, till then your output will be visible. So that's the reason our every program we will find our glut main loop. So based on based on the number of divisions you give, you will actually be getting a Sierpinski gasket in this way. Whether you can start your division from 0, 1, 2, 3, and the more number of divisions. And don't try to give a very larger number of divisions also, because again enabling your updating your depth buffer with a minimum amount of that is a minimal processor, it is difficult. So try giving a lesser number of divisions only, and just see how beautifully our Sierpinski gasket is being drawn here. So again I'm repeating, there are actually four faces here: the one wherein the triangles are drawn in red, the one where it is drawn in blue, the one where it is drawn in black, and this green is back, actually the back face, it is your back face. So in this way, we are using a polygon and a recursion method in this program. We are actually, by using a tetrahedron, we are recursively subdividing a tetrahedron, and we are drawing a or we are generating a Sierpinski gasket. There's also another method called as the random point generation method. I'll share you even that program also with you. So that is another way wherein just by generating the points only, we try to draw a Sierpinski gasket. You can just refer even that also. So this is about your lab program 7, how you can draw a Sierpinski Gasket. So if it is possible for you people, if you have enough resources, please try to execute these programs and try to see how the output looks like. Thank you everyone.